Hi class, this is Professor Smith. I'm going to be doing a movie on hypothesis tests for the difference of population proportions. In this example, we have airlines must be careful about the total weight of baggage carried by a plane on a commercial flight. Passengers with items exceeding the maximum single item weight, usually about 70 pounds, must pay a fee, usually about $50 per item. Airlines continually monitor the proportion of overweight items in order to evaluate the appropriateness of the overweight fees. English Air charges different amounts for overweight items on flights to the US and Canada than it does within Europe. Recently, a random sample of 235 items checked on English Air flights to the US and Canada contained 30 overweight items, and an independent random sample of 300 items checked on English Air flights within Europe contained 52 overweight items. Based on these samples, can we conclude at the 0.05 level of significance that there is a difference between the proportion of all English Air flights to the US and Canada which are overweight, we call that P1, and the proportion of all items on English Air flights within Europe which are overweight, P2. So we want to know, is there a difference between those two? I'm going to open up math type in order to capture what I'm reading in the problem as if I were writing on a piece of paper. So I have here, we have US and Canada, and we also have within Europe. We have that the proportion for the sample that was on the US and Canada was, the random sample was 235, and 30 were overweight. So that would be 30 over 235. So that would be represented with a P hat. But because there's two different populations, that's why we do P1 hat for the first group and then P2 hat for the second. And for the second, it's 52 out of 300. So let's capture that in math type. So we have P1 hat is 30 over 235, and P2 hat is 52 out of 300. Again, it says at the 0.05 level of significance, so that's alpha equal to 0.05. They want to know, is there a difference between P1 and P2? And to say that there's a difference means that they're not the same. That means they're different. And the way we represent that mathematically, different means not equal to. So that's going to be our claim. It's at that 0.05 level of significance. And so that's going to be my clue that that's the part that I'm going to make a decision about based on that statistic of 0.05, alpha equal to 0.05. So the first thing that we want to do is write down the null and alternative hypothesis. We can see in the problem that whenever we have P1 not equal to P2, we know automatically that's going to be a two-tailed, but Aleks also says it too, perform a two-tailed test. So whenever we have different as one of the claims, then we know that it's going to be a two-tailed test. We know that H naught always has the equality, and so that would be P1 equal to P2. And so H1, it does not have equality. So H1 would be the second, and that's our claim. So let's copy that. And we have that alpha is 0.05. So I usually like to capture that in the first step. Step 2 is we're going to be doing a hypothesis test between proportions, and provided that the sample sizes are large enough, then that will let us know if we can use Z. And Aleks is generous and nice, so we use Z because the sample sizes are appropriate. Step 3 is to find the test statistic. And so we can use our formula sheet to come up with our test statistic. So let's open up the formula sheet. When you select the instructor resources icon, you'll see that it says Chapter 11 Formulas. And here are the formulas. And so this is between two means, independent Z, two means, independent T, two means paired dependent, which is paired comparisons. And here's our formula for finding the difference between two proportions. So we have P1 hat minus P2 hat all over the square root of the pooled proportion P bar, and 1 minus P bar, times the sum of the reciprocal of the sample sizes. And you say, well, what's P1 bar? Or P bar, excuse me. P bar is taking the numerators of the two sample proportions, x1, x2, those are the numerators of the sample proportion, divided by the sum of the sample sizes. I tell students in class, it's the first time you can illegally add fractions. And the premise is that if the population proportions are equal, well, the sample proportions should be kind of close to each other. So these fractions are about the same. So it would be, if you did have identical fractions, 2/3 and 2/3, then that would add up, if you add them right across, that's the same as 4/6, which is again 2/3. So that's the premise. All right, so let's go ahead and use math type to fill in those values. Now we have math type open. So the first thing we're going to do is express P bar. And I don't know why, but on Aleks, it seems like sometimes when you convert it to a decimal expansion, there's some errors. So I've been showing students in my on-ground class to just keep it as a fraction rather than approximating it with a decimal, even though you might do it to 4 places or whatever they tell you the intermediate computations to. I would just leave it as a fraction. So for P1 hat, it was 235 out of 300. No, excuse me, 30 out of 235 and 52 out of 300. So to find that P bar, we're going to take the 30 and 52, those are the two numerators of our proportions, and add those up. So that's going to give us 82. And then if you take 235 and 300, that's going to give us 535. So let's do that real quick. Now when we substitute in our values, I'm just going to, again, like I said, leave them as a decimal. So then Z is going to equal to P1 hat, which is that 30 over 235. Minus the 52 over 300. We're going to divide all of that by the square root of P bar, and P bar was 82 over 535. I'm copying that so I don't have to type it again. And then notice when I did that, how the square root stopped showing up. So just be careful on Aleks that you don't slip outside of that radical. So you can't see it, but I just cursored over to the left. And now when I put in the parentheses, you'll notice that the square root expands with it. So then we're going to do 1 minus that 52 over 835. And then I'm just going to use the arrow key to cursor over rather than trying to tab, because I'm not tabbing in the right spot. And then it's just going to be the reciprocal of the sample size. And here are the sample sizes, 235 and 300. So it'll be 1 over 235 plus 1 over Aleks, and compute what that z-score is. So that was the 30 divided by 235, and I'll double check to make sure I'm putting it in correctly. Minus 52 over 300 all divided by the square root of adding the tops 82 over 535 and then 1 minus 82 over 535. Times the sum of the reciprocals of the sample size. So the first sample size was 235, so 1 over 235. That's the first reciprocal, plus 1 over 300, which is the second sample size, and then we have the reciprocal. Notice the square root is capturing the sum of the reciprocal of the sample sizes, and it's also capturing p bar times 1 minus p bar. So make sure that the square root symbol doesn't disappear on you. And like I said, if you leave it as a fraction, for whatever reason, it seems to not cause problems for students. So we get a z-score of negative 1.455. The fourth step after we find the test statistic is to make a decision. So we have to scroll down on Aleks to decide which way we're going to go. And this one is a p-value approach. So to make our decision, we have to first find the p-value. That's z because that's the distribution. And then we take the symbol from the alternative hypothesis. So if we scroll up to the alternative hypothesis, we had that H1 was not equal to. So we want to use that same symbol, not equal to. The test statistic, and that's going to be the negative 1.455. So we have the P of Z is not equal to negative 1.45. So there's two cases that can happen here with the two-tailed test. We can have the probability that Z will be to the extreme left of negative 1.455 or to the extreme right of 1.455. It turns out on the Aleks calculator it's easier to compute the one on the left. And because of symmetry, then it's like, my goodness, why don't we just do the one on the left and double it? So let me show you what I mean by symmetry by opening up Word and using the draw feature. So now I've opened up Word and I'm using the draw feature. And we're going to draw, well, I'm going to try to draw a bell-shaped curve. Now remember, I'm using my finger and a trackpad, so. All right. So that's supposed to be symmetric. So we got a test statistic of negative 1.445. And what I was saying is that finding area to the left of negative 1.455, which would be this region here, the shaded region here to the left, and to the right of positive 1.455, they're the same, they're symmetric. So since they're symmetric, why not just find the easier one using the Aleks calculator? And you say, well, why is it easier? Because the Aleks calculator has that less than or equal to button. So things that are on the left for Z. So then I would just find this one and double it. So it's going to be 2 times the probability that the z-score is less than negative 1.45. And the Aleks calculator says, hey, whether you have less than or equal to, you're still going to get the same value. I don't know why I made that funky looking less than symbol. Let's see if I can fix it. And so let's go ahead and do that now on the Aleks calculator. And I tell students, even if I got a positive test statistic, I just make it negative and do 2 times P. Anytime it's a z-score and it's a two-tailed test. So now I have the Aleks Calculator open. I have the test statistic. I'll double click on that. I'll hit 2 times P of Z, and then I'll put a 2 in front. So you get 2 times the probability that Z is less than or equal to negative 1.455. And we get a p-value of 0.146 when we round. It's going to help us make a decision. So the question that we always ask when we're finding the p-value is when we're using the p-value to make a decision, is we ask the question, is the p-value less than or equal to alpha, where alpha is our level of significance. So whether it's a two-tailed test, you ask this same question. Whether it's a left-tailed, same question. Whether it's right-tailed, same question. Just with the critical value, you always ask yourself the same question. Is the test statistic in the critical region? Well, when we get to the p-value approach, we ask, is the p-value less than or equal to alpha? So regardless of the alternative hypothesis, this question remains the same. So it doesn't depend on the symbol in the alternative hypothesis. All right, so the p-value was 0.146. And our alpha value was equal to 0.05. Let me just make sure. I put it in the null hypothesis. There it is. Yeah, 0.05. All right, so it's 0.05. I always like to add a same number of digits, so I'll add a terminal 0. That won't change the value of the decimal. So I have 3 digits on the left and 3 digits on the right behind the decimal. So it's easy for me to see, oh yeah, 146 is clearly not less than or equal to 50. So that's false. So it is false. So our decision is to do not reject H0, not in favor of H1. In other words, we didn't get anything that extreme. So if we did not get a value that was that extreme, we're thinking, hey, why would you reject that they're equal? I'm not going to reject that. So do not reject they're equal. So I'm not in favor that there's a difference. So our conclusion, which would be step 5, by the way, H1 was the claim. Then we're saying we're not in favor of the claim. And the claim was that they were different, that the proportions were different. So our conclusion would be there is not enough evidence at the 0.05 level of significance that there is a difference in the proportion of overweight bags from US and Canada compared to the ones that are within Europe. So let's go ahead and fill in our answers on Aleks. So we had the null hypothesis is that the proportions were equal. So P1 equal to P2. I tried to use the same steps you do it when you're doing it in math type. You hit Control L for a lower subscript, and so I just hit Control L. It did not work. So sorry. All right, so P1 not equal to P2. And be careful that you don't write the not equal symbol in the subscript. It's Z whenever we have a test between proportions, provided that the sample sizes are large enough to say, hey, yeah, the distribution will be, the sample proportions will be normally distributed. All right, the value of the test statistic, we got negative 1.455. And the p-value was 0.146. And our decision was there's not enough evidence to support the claim or in favor of the claim. So you would say no to the claim. All right, so I hope this movie on the hypothesis test for the difference of proportions was helpful. I'll do another example, but I'll make a separate movie for that one.